Assalamualaikum warahmatullahi wabarakatuh and good day. So now we move to subtopic 5.3, which is parameter estimate, estimation and estimator. So basically in 5.1, 5.2, we are talking about sampling distribution. Okay, the main thing in this chapter for subtopic 5.1, 5.2, we are talking about from normal distribution function, you can have chi-square distribution, you can have T distribution, you can have F distribution. Okay, you can see that overall we consider that if you have big data, you have very big sample size, the population, the sample tu can approximately to normal distribution. Okay, and usually in order for us to make inference about the population, we use sample. Okay, that's why in this chapter 5, you find the sampling distribution in order for you to estimate or to make inference about population. Alright, so now 5.3 is about parameter, estimate, estimation and estimator. So basically you have learned this in applied statistics, okay, in chapter 2. If you remember confidence interval, okay, you make estimate, okay, estimation using confidence interval, okay. But in our class, this subject, you will focus on point estimation, okay. Alright, so by definition 8.1, if you look your textbook, okay, they are talking in chapter 8. The definition for 8.1, an estimator is a rule often expressed as a formula that tell us how to calculate the value of an estimate based on measurement content in a sample. Okay, so for example, sample mean we have y bar, isn't it? So how you calculate y bar? You sum all data, you divide by how many data you have, right? So this is one possible point estimator, okay, of the population mean, because we have mu is a population mean, so sample mean is y bar, isn't it? So this y bar is considered a point estimator for this population mean. Okay, so clearly the expression for y bar is both a rule and a formula. So you can see that, okay, this is a rule and a formula. How to get the y bar? Summation yi divided by n, and it tells us to sum the sample observation and divide by the sample n. So that is the estimator. Alright, so recall, okay, I recall back applied statistic BUM 2413. So you can see that the definition here, okay, the probability function that represents statistical models such as Poisson, binomial, normal, okay, you have one and more parameter. So in our class, in our subject, we not only have Poisson, binomial, normal, we have many hypergeometric, geometric, uniform, gamma, beta distribution. All these, they have their parameter. Okay, so if you look the one previous chapter, in chapter 1 and chapter 2, there is a table that I want you to remember and to look, isn't it? All the common probability density function. You can see the parameter. So the parameter that have been widely used, mean, variance and proportion. Okay, but in our case, we have many others. Okay, shape, okay, scale. Alright, so any function of random sample whose objective is to approximate a parameter is called an estimator. So this is general thing. Okay, that's mean we have this parameter. In order for us to estimate the parameter, we use estimator, which is theta head. For example, just now this is mu, so here will be y bar. Okay, or maybe here is proportion from binomial is p, so here will be x over n. Oh, sorry, this is a pi. Okay, if in previous, this is pi, so we will have p here. Okay, but don't confuse with the notation. Okay, the notation might be different from applied statistic. So this is important. So estimation is the entire process of using an estimator to estimate the parameter. So here we have two types of estimation. We have point estimation and we have interval estimation. So interval estimation, you have done that in applied statistics. That means you just use the formula. Then you look the situation, which formula to be used. You substitute the value, you find the value, the table value, calculate, and then you get answer. Okay, but here in our class, you will prove how this mu become x bar. I mean, how we estimate parameter using x bar. How we estimate this one using s square and so on. Okay. So point estimation, a process that produces a specific numerical value calculated from a sample data representing the unknown population parameter. Okay. So this is the example. Okay. We have many others. Okay. All right. So this is the interval estimation. That means you have two value. Okay. So now the properties of good point estimator. This one very important in our class. Okay. There are 4 main properties of a good estimator, which is unbiased, consistency, efficiency, sufficient. So all this, before this you just know. Okay. But now you will check either this x bar unbiased or not. Either this x bar consistency or not. Either this x bar efficiency or not. Either this x bar sufficient or not. So if they have these 4 main characteristic, that means the y bar is a good estimator. Okay. By the theory, usually y bar is a good estimator for the mu. Okay. But this one in applied statistics lah. Okay. But in our class, you will prove it. How is it? So here, in order to find the point estimation, we have 2 methods to calculate. First, method of maximum likelihood, or sometimes we call it MLE. Okay, maximum likelihood estimator. And then the other one is method of moment. So method of moment, actually you've learned in previous chapter. Okay, we just implement in order to find the point estimation here. All right, so you can see here. This is general term lah. That's mean expected mean theta head is equal with theta. All right, so this one, okay, is unbiased. Why? Because it's similar. I mean, this is your theta head and then this is theta. So this is unbiased. But if you look here, okay, because it's similar, here you also get expected theta. Okay, the theta here, when you find the theta head, you get the same thing. All right, so it's unbiased. But if you look this figure, 8.2, okay, the sampling distribution for a positively biased estimator, because you can see this is your expected theta head should be here. But then you have here. So this one is greater than this one. So it's positively biased. Okay, so if bias is not good lah. Alright. Now, definition 8.2. Let theta head be a point estimator for a parameter theta. Then theta head is an unbiased estimator if expected theta head equal to theta. Okay, so unbiased estimator if expected theta head equal to theta. This one very important because in the question letter, okay, you will check this y bar is unbiased estimator or not. Okay, so you will use this definition 8.2. If the expected theta head not equal to theta, so theta head is to be biased, which is a not good properties of estimator. Now definition 8.3. The bias of a point estimator theta head is given by expected theta head minus theta. So this one to calculate how many bias, how much bias. So you can have the bias by finding expected theta head minus theta. So you can see this figure 8.3. All right, so you can see that sampling distribution for 2 unbiased estimator. So if you look A here, estimator with large variance. So you can see this is your theta. This is your theta 1 head. But you can see the curve here is symmetric like this. Not symmetric. It's semicircle. Okay. So this is quite big variance. Okay. Because it's dispersed and it's big like this. But if you look B here, you have theta here. And then here is theta head. And this is the curve. So you can see that the variance here is small. Because you can see it's steep. Okay, it's thin, okay, compared to this one. So this one is better compared to this one. Even if in applied statistics you have learned, isn't it? The small variation is very good compared to the large variation. Okay, but here you will learn the more theoretical things. Okay, so now definition 8.4, the mean square error. So sometimes we call it MSE. So MSE, the mean square error of a point estimated theta head can be calculated as this one. Right, so MSE theta head equal to expected theta head minus theta square. Okay, so the definition is very important. You will use it later, okay, in example and also in proving. So here notes, if beta head denotes the bias of the estimated theta head, so it can be shown that your MSE will be equal with variance theta head plus bias theta head square. Okay, this one is important as well, right? So this is the exercise, page 394. You can try and look. Okay, I think it's just application exercise. Okay, so this is just introduction, not yet the very theoretical things, but you should understand what is parameter estimate, estimation, and estimator. We have two methods to calculate, which is method of maximum likelihood and method of moment, and we focus on point estimation. Okay, so this is some definition that is very important in order for you to use it later, okay, in the next video. And then you can try lah exercise. If you have problem, you can ask me. Thank you, class.